So we know now what is a transistor. What kind of valve? It's an electrically controlled current valve. Well, it's not a water valve. It's not a fluid valve. It's a current valve. We can operate it in three regions. What are the three regions? Active. Right. And of course, when we operate it in a switch, we're switching it between cutoff and saturation, right? When we operate it as a amplifier, we're operating it in the active region. And we started off with two battery bias. So we had a VBB and a VCC, which you very seldom see. And then we moved into a single power supply bias, which is where we was at. Then we looked at the three ways we can bias it. What's the three ways? Three methods. Saturated switch usually uses a base bias. What's the other ways? Yeah, so we have base bias, we have emitter bias, I should have said four ways, and then a voltage divider. Voltage divider is by far the most popular used for amplifiers, and of course base bias is the most popular used for saturated switches. So these are some pictures of base bias. These are in your textbook, wherever my textbook is at. Collector bias, and then voltage divider bias. Now, voltage divider bias, this is what's really neat, because what we use in voltage divider bias is basically we use only the formulas right now that we learned in what class? DC. And what you do when you start calculating this thing is you picture two individual series circuits. You picture a series parallel circuit, actually. So what you do, if I was to look at this thing, of course, I've done it so long that I can see it in my head. But normally what you do is you come over here and you look at this like this. So you look at this as R1 and R2, and you look at this circuit going to VCC, and you do it. So you calculate that just like a series circuit, right? You understand? And then what we do is we look at this circuit by itself, and we calculate this. And what we're going to do is I'm drawing the transistor as a rheostat. So this guy right here sets a voltage that we call VB, right? You understand? So when I calculate VP, I just calculate the voltage drop across R3. Then what do? Well, we come over here and we say the voltage drop across this resistor is equal to VB if it's silicon minus 0.7. That's what we do. And then what do? We use that voltage to calculate what we call IE. And what does IE stand for? Okay. And then we use IE. We're using this right here, even though that is not true. It's close enough that we can use it because everything we do is approximations anyway, right? You understand? Then what do? Well, we do that to calculate. So IE and IC are basically in series with each other. So what we do is we use that to calculate the RC. So we call this resistor generically, we call this RC, and we call this RE. And then we calculate voltage collector to emitter by what? We take, we calculate VC. VC is going to be equal to what? VC minus VRC. That's Kirchhoff's law, right? You understand? Then we're going to use VCE would be equal to VC minus VE. And all we're doing is what laws? We're using the laws that you learn in DC. But this looks like a series parallel circuit, or two series circuits that are in parallel, but that's all a series parallel circuit is. Now, most of the time, this is a type of series parallel circuit you run into. In DC, we put some more complex ones, right? We'll put a series resistor here and a parallel branch in the center and then a series resistor. You don't see those very often, but that's just to prove that you can calculate that thing. So this is nothing but what we learned in DC. But what we're trying to do is we're trying to establish something that we now we call it what? We call it bias. And what is bias? These are test questions. What is bias? This is a DC voltage we apply to a semiconductor device to set its operating characteristics or parameters. That's what we're doing. So what we just did is we biased this transistor in the active region. And now it's biased in the active region. Now it can amplify, right? Now this guy right here, this is called common emitter. Now when we talk about, we have three ways we can hook up an amplifier. We can hook it up common emitter. What would be the other two ways? We got three leads. So common emitter, yeah, common base, and common collector. And this, we're looking right now at the common emitter. Now, when we're talking about common, has nothing to do with DC. It's how it's set up common to the signal we're going to put into this thing. So here we're bringing the input in on the base. We're taking our output off the collector. So the emitter has to be common. Now here it looks obvious because the emitter is connected to common. So this is a common emitter amplifier. And we can definitely get voltage gain out of this guy. Definitely. And what we have set up here, let me pop up my camera, is the circuit that we set up last night. So here's the circuit hooked up. Took me how long to hook it up? I did it while y'all was solving the circuit, right? Then what we're going to do, in fact, we get so much gain out of this thing, I can't get my amplifier to trigger on my input. So I have these two channels set up exactly to the same voltage level. And I'm putting a sine wave into the thing. And normally when we troubleshoot audio amplifiers, we like to have a function generator so we can put a sine wave into it. Even though these guys are set up to amplify audio is all over the place, right? But if we put a sine wave in, then we can look at the actual gain. We can look at what we get in and what we get out. So the other one here, this is channel 1. It's on 5 volts per division. Sorry. I tried to set them on the same. So channel 1 is on 2 volts per division. Thank you. Now let's make that puts it trigger. And this is on my base coming in. This is on my base input, which would be on the other side of my capacitor. And then the blue one is the output. They're both set to exactly the same range. So I have it set on 2 volts per division. So roughly we're putting in about, of course, if I wanted to measure this, I would get more accurate. So we're putting about 1 volt in, and we're getting 1, 2, 4, 6, 8, 10, 12, over 14 volts out. I mean, that's what we get out of the transistor that we can't get out of a diode. We can't get out of resistors. The only thing resistors will do is drop a voltage, right? Now, what you have to understand, I'm going to move my my input. I'm going to move it actually onto the base of the transistor. I'll try to. Okay. And I'm going to set my back to 0. So you can see the input signal is actually riding up on that DC bias, and that's what we're doing. Our input signal is varying the DC bias, right? You understand? And then of course, if it varies this DC bias, it affects the voltage drop across RE, which changes the current flow. And if I look at the output, which is going to shift way up. So here's actually the output of the transistor. Oops. Yeah, we got it on AC coupling. Let me put it on DC coupling. It's still on DC coupling. There we go. So you can see my inside the transistor amplifier itself, all we're doing is changing these bias levels, right? You understand? So what we end up with is we end up with AC actually superimposed on the DC bias. Does that make sense? And what do we do? Well, what do we do to get AC into the DC bias and get AC out of the DC bias? What do we use? We use capacitors. So if we use the right size capacitor, then one of the things a capacitor do, once it charges, it blocks DC. So what it does, it lets AC come in and couple in with the base bias, right? You understand? And then it lets this AC, this AC superimposed on DC out here. It allows us to bring it out of the amplifier. So all I'm doing is just moving on to the other side of the capacitors. So here we have the AC, and then here we have AC across our load. So that's what that's the fun. We call those coupling capacitors. So these capacitors have names, and you can see how these got that name, right? Because what do? They allow input to couple into the amplifier. Here we have DC, here we have AC. So it lets the AC come in and prevents the DC bias from doing what? Getting out, right? Okay. Over here, we bring this in. Now notice the polarities are very, very important because these are polarized capacitors. Over here, what DC component does AC? What DC component does AC have on? Let's go back. What's the average? What's the DC average of an AC cycle? Huh? 0. So that means this is considered to be DC 0, right, or ground. So DC sees an AC source as a ground. So this is, well, I forgot about 2 volts. So that means this is positive in relative to the AC input because true AC is considered to have a 0 volt reference, right? Y'all understand? Now we come over here, it depends on, I'm hooking this up to a resistor. The resistor is connected to common. So right now, of course, later on, guess what we're going to do? We're going to hook it up to another amplifier. What we usually do when we do amplification is we like to go through stages because the more gain one amplifier has, the noisier it is. So usually we go through multiple stages. If you're familiar with stereos, we have a section we call a preamp, and that's where all your tone controls are at, where all your balance controls. And then the preamp feeds into another section that we call the power amp. And the power amp is where you get all your power gain, right? So what we do is we usually go through stages. So later on what we're going to do is we're going to take this and hook it up to another one of these. And this right here, what was the gain on this? How do we calculate the gain on these right now? We take this and divide it by that. So right now, this guy here would have a gain of 10. But, the book, I hadn't looked at this book. The other book that we had, which was the same book, they didn't tell you how to do the gain if the amplifier is loaded. Now, if we load this thing, so this guy's going to hook up to something, right? Y'all understand that? And as soon as we hook up to a load, what would you expect the gain to do? Would you expect it to go up or go down? Down. So what we do, so let's say I come over here. Let me bring up the PowerPoint. Now, the output of the circuit is generated right there. So that's where it's generated. So if I came over here and I put a load on this thing, Let's say I come over here and put a 10K load right there. Now that's going to have to gain. So our output is generated at that dot right there. So the way this sets up is we come into the amplifier. This is what your AC sees. And we see R1. So my AC comes in here and goes this way. Now we're drawing this signal flow, not current flow. It gets real complicated if you try to draw everything from ground. But there's a dot right there. What does that mean? So that means my AC is also going to go what? It's going to go that way. Now, what does AC see a DC power source as? It sees it as a short circuit. It'll fly through DC just like it wasn't even there. So what your AC sees is it sees this. This is the circuit it sees. This would be R1 and that would be R2. That's what AC sees right there. And then it'll come over here and it'll see the diode junction. And then it'll see RE. Now you got to understand this transistor has a beta. And typical beta for a 3904 is what? We've already talked about that. So we're using a 2N 3904. Typical beta is 100. So that means if I put, let's say this is a 1K over here. So that means if I put 1 milliamp of current flow through here, then this guy is going to see it as 100 milliamps. And actually it's going to be a little more. Y'all understand that? Now, if I was to come over here and take 1K and multiply it by 1 milliamp, which is what your input sees, then it would drop 1 volt. Y'all follow me so far? But the transistor's got that gain. So what's going to happen is if this is 1K and it's going to see it as 100 milliamps. So how many volts is it only going to drop? Actually going to drop. $1K, 100 milliamps, 100 milliamps, I'm sorry. How many would it drop? Ohm's law, guys. Come on. 1K times 100 milliamps. V is equal to I times R. Now we're just talking, so what is it? What would it be? Huh? Okay, so it's going to drop 100 volts. So your input, if this was 1 milliamp, if I put 1 milliamp right in here, of course we're right here, right? Y'all understand? This guy here should drop 1 volt. But when I put 1 milliamp over here, it drops 100 volts. So your input does not see that 1K resistor over there. It thinks it's 100. So 1 milliamp over here, this is what your input sees. So your input sees 1 milliamp. Now, when it puts that 1 milliamp in, that resistor over there would drop 100 volts if we got a beta, right? You understand? So what would it be? So if I came over here and I say R is equal to V over I, and I say R is equal to 100 volts divided by 1 milliamp, because that's what your input is seeing, right? You understand? What size resistor is it? What size resistor does it see? Your input does not see 1K. Your input thinks it's running into this guy right here. What's that? Yeah, so it thinks it thinks RB is equal, it thinks RE is equal to 100K. But it's not. It's equal to 1K. So your input, your AC input sees RE as times beta. So it's going to see this as a watt. It's going to see this as a 100K resistor. If it's a 1K, it's always going to be times beta. Y'all understand why? Yes or no? Make sense? So normally, so what do we got over here? We have 100K in parallel with a 10K in parallel with another 100K. That's what your input sees. Now, where's your output at? Well, your output, what we would do is this is going to be a current source over here. And then what my output sees RC in parallel with RL. That's what the AC, RL, Rich. That's what the output sees. So it actually sees two different circuits. It sees the input circuit, which determines the amount of current we put into the thing, and the output current circuit, which determines how much we get out. So RC would be equal, so this resistance right here would be equal to 5K ohm if I load it. You understand? Yes or no? So what would the gain of this circuit be? Well, instead of being a gain of 10, it's going to be a gain of 5. We still do it the same way, but the voltage gain formula for this is actually A. So we use A to represent what? Gain. We've already talked about this, right? Okay. And D would be equal to what? Voltage gain would be equal to R out